Hi and welcome to this video on trends in atomic radius. So what we're going to look at in this video is about what those trends are and therefore why they are occurring. So first off, a definition or two. We're going to talk about both atomic and ionic radius over the next couple of videos. So some definitions first off. The atomic radius is the distance between the nucleus of the atom and its outermost valence electrons. Okay, it's got nothing to do with what's happening on the inside, it's the outermost shell of electrons. And the same thing for the ionic radius. These radii, that's the plural of radius, are measured in picometers, which is 10 to the minus 12 meters, 0.000000000001 meters. Typically, we've got around about 1 to 200 picometers is the radius for most atoms. Okay, so the radius of an atom is dependent on two things: the number of protons in the nucleus and the number of shells of electrons that surround that nucleus. So the more shells of electrons we have, it makes sense to think that the further away from the nucleus they're going to be. And if you go back to that animation in my first video about electron configuration, you will see very quickly that the more shells you have, the bigger your atom is going to become. But the other focus, or the other thing to consider, is the attraction between the positively charged nucleus and the negatively charged electrons. So the more protons you have in the nucleus, the greater they are going to be attracting the valence electrons towards that nucleus. So you've kind of got these two competing factors. You've got the repulsion between the electrons, which means that the more shells we have, then the further away from the nucleus it's going to be. But then you've also got the attraction for that nucleus. So there's sort of attraction and repulsion going on at the same time. So what are the trends that we need to look at? Personally, I think this periodic table illustrates it really well. And so there's two different things that are occurring if we look at this periodic table. And so what we're seeing is as we go from left to right across the periodic table, I hope you can see that the radii are decreasing. It's getting smaller as we go from left to right across a period. So if that particular arrow is sitting on the third period, as we're going from left to right, it's getting smaller and smaller and smaller. As we go from top to bottom, down a group, the radii get bigger. And those are the two trends that we need to explain. Okay, so as we go from left to right across the periodic table, the radii decrease. As we go from top to bottom down a group, the radii increase. And this is because of the electron configurations and the number of protons in the nucleus. That is the sole and only factors to consider: the number of protons and the electron configuration. So let me break this down one trend at a time. If we look at these two trends, we've got the two trends that the radius increases as we go down a group. And the reason for that is as we go down that group, each element has successively more electron shells or energy levels, which are further away from the nucleus. The further away they are, the greater the radius becomes. Let me just show you what I mean. If we think about that first group on the periodic table, our first element is hydrogen, and its electron configuration is 1s1. If we then jump down to the next one, below hydrogen we have lithium, and its electron configuration is 1s2, 2s1. Right. So you can see already we've got an extra shell of electrons on there. Hydrogen's valence electron is in the first energy shell, lithium's valence electron is in the second energy shell. If we continue going down, then we get to sodium, and sodium's electron configuration is 1s2, 2s1. 2s2, 2p6, 3s1. So down further. So now you can see that we've really got a lot more electrons. So we've got 2 electrons in the first energy shell, 8 electrons in the next energy level, and then 1 electron in that third energy level. So we've got a lot more electrons. Those electrons are all repelling each other, pushing those valence electrons further away from the nucleus. So even though we've got more protons in the nucleus of sodium compared to lithium or hydrogen, the electrons are still going to be that much further away, which is why it's bigger. And finally, we can do the same thing again with potassium. This electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And again, the number of protons is increasing, but so is the number of energy shells. So they're just going to be that much further away from the nucleus. Now a different kind of process is happening when we consider what's happening as we go across a group. So let me show you what happens there. If we consider the trend that as you go from left to right across the period, the radius decreases, the reason for that is because the valence electrons are staying in the same energy level. But the number of protons in the nucleus is increasing, which increases the attraction between the valence electrons and the nucleus, therefore reducing the radius. So let me show you what I mean by that. Right, so if we start off, if we think about that third period, we've got sodium, which has 11 protons. Its electron configuration is neon plus 3s1. Okay, I'm just using that shorthand where we go back to the nearest noble gas, and I think that that's just going to make life easier. So sodium has 11 protons, it has 1 electron in that third energy shell. If we then consider, we'll jump across a little further and we're going to look at aluminium, and aluminium has 13 protons, and its electron configuration is also starting with the neon configuration, and we're going to go 3s2, 3p1. And so there are more electrons in that valence shell, but they are no further from the nucleus. The fact that you've got more protons in the nucleus means you've got a greater attraction between the nucleus and those valence electrons, which is going to pull those valence electrons closer to the nucleus, therefore decreasing its radius. And we can see that if we go even further across the periodic table. So if we jump over and we think of sulfur, sulfur has 16 protons. Its electron configuration also starts with neon, 3s2, 3p4. And so again, you can see that the electrons that we're not adding extra shells on, we're putting more electrons into the same shell, but we're not adding any extra shells on, but we are putting more protons in the nucleus. We're getting more attraction, therefore pulling those valence electrons closer to the nucleus and making that atom smaller. That is explaining the trend. Okay, so the sorts of questions you might expect to see. You might get asked to explain or compare or discuss the differences between the radius of 2 atoms. Those 2 atoms will be in the same group or the same period. If they're in different groups and different periods, then you would be given data about them. And in all cases, your explanation is going to refer back to those 2 key factors. What is the number of protons in the nucleus? How many shells of electrons are there? And how do they compare? So, for example, if we're comparing the radius of chlorine and sodium, we can say that as we go across the period, the number of protons in the nucleus increases. They have the same number of energy shells. The valence electrons are in the third energy level in both cases. You could draw out the electron configuration as well, and therefore there's going to be a greater attraction between the nucleus of chlorine and the valence electrons, causing that radius to decrease when compared to sodium. Depending on how the question is phrased and exactly what's being asked, you may need to change that answer slightly, but it's always going to come back to those two factors. How many protons are there in the nucleus, and how many shells of electrons are there? If there's more shells of electrons, those valence electrons are going to be further away. If there are more protons in the nucleus and the valence electrons are in the same shell, then it's going to be smaller. So always consider those two factors. All right, I'll see you in my next video where we talk about the difference between atomic and ionic radius. See you then. Bye.